All good? Great. As they mentioned, my name's John Stratton, and I wasn't sure how much of an introduction I was going to get. So, quick review again. I got a PhD in electrical and computer engineering, so not exactly computer science, but certainly very hardware, very systems focused under Wenmei Hu. And I've been affiliated with Multicoreware since 2010. Currently, hold the position of CTO there. I'm a computer science professor at Whitman College since 2016, and my research area and professional work overall generally focuses on software design and performance together. And I want to spend about the first half of my talk or so talking about you know the big trends and the big ideas there that aren't specific to C++, but try to highlight why is software performance and software design important today, and then a little bit of a case study of how that plays out in some software projects that I've been working on more recently. So going back to performance in ye olden days, you had computers from IBM, DEC, and Apple over 60s to 70s, and over time, what you saw here was just dramatic improvements in the underlying technology. So you had cost going down by orders of magnitude more than every decade. You had the size of memory. Well, the size of memory went down a little bit so that you could fit it into, on a desk rather than in an entire room. But then on the other side, clock rates and frequencies were going up orders of magnitude as well. Just manufacturing technologies and semiconductors enabled us to run these processors faster and faster over time. So, but just despite those dramatic improvements over time, you look at these computers by not just today's standards, but by any real standards, and you have to start asking yourself, how do we get these to do anything useful? The entire memory available to the Apple II machine was 48 kilobytes. That was your entire RAM storage. And most of us in modern applications will blow through that without blinking an eye. Like, that is just background data that we need to do the bare minimum. So think about what you could do with meaningful data sets with 48 kilobytes of data. The answer is not much. And since that is all of your randomly accessible memory, when you're working with any meaningful amount of data, you have to assume that it doesn't fit in memory. And so a huge amount of the software development effort that was being spent in these days was carefully and explicitly moving data between your permanent storage, floppy disks, hard disks, tape storage, and your very limited short-term memory, like these 48 kilobytes of space that you have here. In order to make these work at all, you basically had to plan what computation you wanted to do around the capabilities of the machine that you had in front of you. You knew exactly what this 48 kilobyte limit was, and you needed to make sure that your program was written to account for that constraint explicitly. And you also had to be very careful with instructions because, 1 megahertz sounds like a big number, but compared to today's standards, it was very, very, very slow. And so even instructions and programs, individual operations needed to be considered very carefully. And just in general, computer science and programming in these days was heavily steeped in performance engineering. Most of your work was spent not just designing the right algorithm and organizing your software elegantly, but making sure that you could squeeze every bit of performance that you could out of these machines. Thankfully, those days did not last. There was a wonderful period of time from those early days of computing until about the mid 2000s, where we had what I would describe as ideal scaling. This was the period of time where the hardware manufacturers got better and better, and we were able to put more and more transistors economically on a single chip. We were able to run those transistors at higher and higher frequencies because it was possible to, when you have a transistor get smaller and smaller, it turns out that in those early days, the number one limiter on frequency was basically electrical inertia. You needed to, if you had bigger transistors, it took more time and more energy to get them to move or change state quickly. And so as they got smaller and smaller and smaller, we were able to move them, transition them, toggle them faster and faster, and get higher and higher clock frequencies out of it. And as a result of those two things combined, more transistors running at higher speed, we got a dramatic improvement in software performance over this time. And it wasn't just, from before until then, we had more performance. It was anyone living during this period of time was living in an environment where if your performance was not that great right now, you could just wait a little bit. And in another year or two, if you had an application that was not quite fast enough right now, you could just wait a year or two, do nothing, and suddenly your application would be fast enough or a lot faster. So let's put yourself back in that time period and imagine that you're managing a software company in this era, and you're considering a new feature, but it's a bit too slow. Given that it's a bit too slow, your options at this point are you can make your programmers try to fix it. You can say, I want my engineering staff to spend their time and effort on improving the performance of this feature, however long that's going to take. Maybe they don't have the skill set to do that. Maybe you'll need to hire some performance engineering consulting experts to fix it, which is going to be more expensive than just telling your engineers to figure it out, but maybe you've got a higher chance of success there. Or maybe you just wait a year and the problem just goes away. And during that year, you get to work on other things. You get to work on other features that are also important and maybe not as performance sensitive. And the performance sensitive feature that you were working on, you just wait a year to roll it out, and then everyone's computers are faster and everything goes fine. So think to yourself, what would you do in this situation? I mean, it depends on a lot of things and a lot of factors, but you have to realize that, at this time, waiting a year for a feature that is maybe not essential and just going and working on something else sounds very reasonable, especially when you consider all of the other things that you might need to do as a software development company, such as, for instance, um, you know, if you cared about things like good design and good implementation, this was the time that people really started caring about software design and realizing that if we need to build bigger and bigger computing applications, you had people like Michael Jackson who were working on how do we build bigger and bigger software systems, given that we have more and more computational power and more complex things that we want to do in our applications. And given that those were big problems that needed to be solved, it turns out that the prevailing wisdom of the time came out to some very famous quotes like the first rule of program optimization, don't do it. And the second rule of program optimization, for experts only, don't do it yet. Wait until you actually know you have a performance problem and then maybe spend a little bit of time trying to fix it. But by and large, we've got better things to do as software developers. Donald Knuth, who won a Turing Award in the 70s and had a lot of contributions to the field. Premature optimization is the root of all evil, or at least most of it in programming. And then one of my favorites, more computing sins are committed in the name of efficiency without necessarily achieving it than for any other single reason, including blind stupidity. So, this is what the computing luminaries of that time had to say about software performance optimization. And they were reacting to this idea to say, no, we are moving away from the era of the 60s and the 70s where you have to care about performance deeply and pervasively to get anything done. And they are trying to help people understand that we are moving into an era now where that is not how we should be treating performance. We should be treating performance as one of many concerns about our software systems, and often not the most important one, given that performance is just coming at us for free from the hardware people. That transitioned in the mid 2000s because mainly because of this line right here. You'll see that the amount of power that we were starting to burn on these computer processors was getting to the point where it was not reasonable to cool them effectively or efficiently. And so, because of that limit, we had to start limiting the frequency of our processors. But the hardware people were still doing great and were still just giving us more and more transistors. But we were running out of ideas of what to do with those transistors to make one CPU core go any faster. And we weren't able to run those transistors at much higher frequency because of our power limitations. And so what happened was we converted all of those extra transistors into multiple cores. And so we had the multi-core era of computer processors. And when parallel processors for things like GPUs and graphics processing units and things like that really took off. So software performance in this era primarily came down to, well, we are limited by power. Things are not going completely smoothly, and we aren't getting new performance for free. So you can see here, we were getting some performance improvements in single thread applications, but not nearly as much as we were before then. So in this era, this is the era where we had the emergence of a lot of new software tools for things like making parallel programming, multi-threaded programming easier. You had CUDA, C++ threads, Silk, all of these things getting added to widely used programming language is even when we cared about performance. We had frameworks for enabling massively parallel cloud computing. This is when frameworks like Hadoop came into being. We started developing everything around REST APIs for cloud-based and web-based services. We started seeing parallel libraries being developed for specific domains. So we see things like OpenCV for computer vision, X265 for video encoding, Torch for early machine learning and neural network applications. All of those things were getting developed around this time. And Multicore, where the company that I was working with had their hands in a good number of these libraries. But the prevailing wisdom of this time was just make your code parallel, and then you get to just keep scaling. It's not free. You need to do something, and that something is make your code amenable to this parallel execution environment. But if you can do that, then again, performance is more or less free. You just keep scaling from there. Then something happened. This is not a firm engineering or technical report, but it is an interesting data point. So this was Intel's roadmap in terms of their process scaling, and that orange line is Moore's law. This was the law that everyone was following in terms of putting more and more transistors onto a single chip. And getting them to be smaller and smaller in area and faster and more efficient. You can see that that line goes great for decades. Doesn't the data that I had from this source here doesn't go earlier than the mid 80s, but you can see over this period of time things were going great until about 2015 to 2017-ish. Somewhere around in there, Intel's roadmap suffered somewhat of a loss. It took them a lot longer to roll this out than they used to roll out the next shrinking processor node compared to previous years. Some of that is just one company, and there were a lot of improvements that they were making during this period of time. But you can also see how it wasn't just a blip that they then got back down to and recovered from. Like, this is now the new trend line that is offset from where we used to be. People have been arguing a lot about whether or not Moore's Law continues to operate and function today as it used to. I think there's more hype about it than reality. Some of this is more marketing data than real engineering and performance data. But at the same time, we are all, as an industry, coming to understand that even this is being bought at a cost. If you look at this chart compared to the amount of research and development money that needs to be continuously spent to keep up this rate, it is also growing exponentially, and we're not going to be able to keep it up forever. So, whether it's starting now or in the near future or whatever, future hardware progress is not going to match historical rates much longer. It may have already been begun depending on who you start talking to now. Meanwhile, around that same period of time, this is a graph of advancements in machine learning systems and the size of the models that we were using for machine learning workloads around the same time. And you can see that this is, again, an exponential scale. And over that same period of time, since about 2015, we have had a 1,000 times growth in the size of machine learning models just in 4 years or so. So that is, close to 10x a year in terms of size and growth of demand for computational resources. This is just machine learning. Obviously, that is a very big and very important workload overall, but it's certainly not the only one. And we're seeing increased demands for software performance today compared to years previous in a lot of different contexts. So, where does that leave us? Well, today, you could have something like my laptop, an Asus VivoBook M1603QA, which is a couple of years old at this point, and it runs a 3.2 gigahertz clock with 12 gigabytes of memory. Cost about $800. It's got a pretty wide data path. We use vector SIMD widths, but that laptop is now operating in a compute environment where the things that people want to be able to do are to run Llama, Gemini, GPT-5. These models are, remind us, how many gigabytes of data? This is 10 to the 13. Many new applications are straining machine resources. Applications are now, especially machine learning applications, often have to be planned around the machine that you're running on. And a lot of applications are not going to fit on the machines that we want to run them on without intense performance engineering. This is starting to sound a lot like the bad old days of computing, where performance was a top tier concern of software developers. There was a time when the prevailing advice of the community was, don't worry about performance very much. There are other things that we really need to deal with. Now we're in a time where performance is now starting to be a top tier concern again. For energy consumption reasons, the growth of electricity consumption in data centers is increasingly concerning from an environmental and electricity production standpoint. There is a lot of concern about whether the programming languages that people are learning today, Python and things like that, where it's very easy to write very inefficient code. How inefficient? I'm not going to do the live demo today, but I've done live demos in the past where you can easily show that someone can write a Python program and then end up writing a well-optimized C++ program that is 10,000 times faster than the original Python program that was written. A lot of that is performance mistakes that could have been fixed in Python or in any other language. But at the same time, it shows you how easy those mistakes are to make and how much we need to pay attention to performance. And one of the things that you can do in paying attention to performance is, as a first step, choose a programming language where performance is a primary concern. And so with that, I want to move into a case study on exact stochastic simulation. This is a research project that I've been working on for simulating biological systems, and we'll get into the motivation for that here. So stochastic system biology simulation is an application where the primary simulation loop looks something like this. You have a list of things that could happen. These are generally chemical reactions that could take place, but they're not like giant beakers of reactants being mixed together. We're talking about a couple of protein and RNA molecules floating around here and there. So given that, you've got a list of reactions that could happen in the system. And since these are so small, random effects really matter. So we actually need to simulate this as a discrete event simulation, where one event happens at a time over time, so that we can see by running multiple simulations what the effect of random distribution is on how the system behaves overall. And so we have a system where the primary thing we need to do is, from this collection of things that might happen, we need to pick one at random, but not uniformly at random, because each one has its own probability of happening, its own weight of being selected. So we need to do a weighted random selection from this collection. And then after we've done that selection, a reaction happens, which changes the number of different kinds of molecules that you have in the system, which means that we need to then update the weights of the various reactions, because now some reactions are more and less likely to happen than they were before, given what was just consumed and produced with the previous event. And these can get pretty big. It's fairly easy to get 10 to the 5th reactions, and that is a typo. It should be more like 10 to the 10 events that you need to simulate. So this needs to be fast and efficient. So I, working with some research collaborators, started working on developing a weighted random selection library in C++, because this is not something that is well supported in existing programming languages and standard libraries in C++. So we need a dynamic weighted random selector, which I'm not going to go into the math details here, but basically we need to do two things. We need to say, given a pool of things, each of which having a weight, randomly pick something from the pool with a probability proportional to its weight. And then we need to set the weight of a given item to a new value. And we need both of those to be efficient. Now, if all you cared about was algorithm design, you would go into this and say, okay, how can we design an efficient data structure to algorithmically do this with a low asymptotic complexity? And I'm sure many of you have thought about something like that before. The data structure that we came up with, the abstract data structure, is what we called a weight sum tree. So it's a complete tree, a complete binary tree, where every node is going to store the weight of the items stored at that location and the sum of all of the weights in its subtree. So here we normalized all the weights to 1 so that they reflect probabilities. There's more complexity to that, but for the simple example here, we'll assume the weight of this node is 0.1, and the sum of the weights of everything rooted at this node is 1. This node over here, we can see it has an individual weight of 0.2, and the sum of all of the weights in its subtree, 0.2 plus 0.2 plus 0.1, is 0.5. The leaves, those are always equal to each other. Okay, so the way that we are going to do random selection on this data structure is to generate a random number between 0 and 1, a uniform random number. And then what we're going to do is ask ourselves, is this random number that we generated smaller than the weight of this node? If yes, then we will select and return it. If not, though, then what we're going to need to do is to say, okay, we're not picking this node. Which direction do we want to go down the tree, left or right? And we're going to make that decision by saying, oh, well, let's look at the total weight of everything in the left side and see whether that total weight is enough to get us to the number that we had generated. If yes, then we'll go left. Otherwise, we'll go right, with an adjustment to the number that we generated so that this number is still guaranteed to be less than the sum of everything that's in this subtree. And then in this case, we would compare against this weight again. It would still be too small. And so then we'd end up going down the tree and picking this item down here. Okay. So this is a weighted random selection algorithm that is logarithmic with respect to the number of things in the data structure because it's a balanced binary tree. Looks great. The problem, though, is, well, not all distributions are equal. And in fact, most of these applications have distributions where some weights are a lot bigger than others. And if you look at this data structure, the amount of time that it takes us to pick something out of this tree really depends on how deep the thing that we are selecting is. Which means that if we can put the heaviest things at the top of the tree, we might be able to do a lot better in terms of how quickly we can find things that we're looking for, if the things that we are most likely to select happen to be near the top of the tree. So let's apply a heap ordering to this. In this case, a max heap ordering. So we'll put the heaviest things at the top of the tree, and then that will allow us to be more likely to more quickly find the thing that we're selecting, because the things most likely to be selected happen to be at the top of the tree. In order to do that, we need some extra data structure stuff. We need an ID table that tells us for every item, which node in the tree does that item correspond to, because it's not built into the position in the tree by itself. And so we need lookups in both directions. We need to know for every position in the tree, what item number is this? And then for every item number, where in the tree does it belong currently? So we need relocation data for that. So that brings us to the software design challenge. We actually need, in this application, a couple of different data structures. We actually need an indexable priority queue as well, which is also not part of the C++ standard library. And we also need a heap-based weighted random selection, which we think is going to be faster. But, maybe we also want to test a standard weighted random selection to see whether it's going to be just as efficient and, the overhead isn't worth it. Well, the problem is we now have kind of three things going on here. We've got a weight sum tree, which is a property or a tree that stores the weight of items at each node in the tree. We also have a heap, which says a heap is a property that you can apply to a tree that will make sure to order things in the tree according to some value. And then we have this other feature for like tracking the identifiers of nodes in the tree, so that as things move within the tree, we can actually track which item went where and also do lookups to say, oh, I want to look up item number 15 in the tree. Where is it currently, given that it's been moving around? And you could also imagine a variety of different data structures underneath for storing this. Abstractly, we draw it as a tree with nodes and edges, but that could be an actual linked tree data structure with nodes and pointers, or it could use the array implementation of a complete tree that you might have seen in a data structures class that can be more efficient, potentially. But the problem is that each one of these intermediate features has some methods, it has some code associated with it to implement algorithms that don't really care exactly what you're doing. You just need an algorithm to do this. And then we have concrete classes that are going to need to combine a mixture of these different features. So you might look at this and say, okay, these are all the classes that we're going to need. We're going to need some base class for the tree data structure. We're going to need a couple of different interface type classes for different features that we might need to mix in and add to a tree. And then eventually we're going to need some final concrete classes that implement a heap-based weighted random selection abstract data type, or a priority queue data type, or an indexable priority queue data type, and so on. Okay. So let's take this and figure out how we're going to make this work in C++. The first thing that you might think about is to say, okay, C++ supports templates and multiple inheritance. So let's go through, and as an example, let's use a weight sum tree. So this was the weight sum tree, the tree where every node has to store its own weight, its own value, but then also store the sum of everything in its subtree. Okay, we don't know what the underlying data structure is going to be, so we just know that whatever implements this interface has to give our functions. So our functions for implementing this interface are going to be updating a weight, getting the total weight of the entire tree, swapping items around, which you need to do specifically because if you swap two items, you also need to maintain and update the weights of those items and the weight sums of those items as you swap them around. And then you've got the operator to do the weighted random selection. So these are all important methods that might be implemented in a variety of different subclasses. So we want to have them in a common base class here to exhibit good design and not duplicate code where we don't need to. But in order to implement these functions, whatever derived class is providing us a concrete tree data structure to do this kind of stuff on is going to have to give us these hooks, these functions to use inside of the code that we use in these functions. We need to know whether the tree overall is empty. We need a way to look up the root of the tree quickly. We need to be able to, given a position in the tree, look up the weight and the weight sum of the node at that position. Okay, that works. We have virtual functions, and then the derived classes can just implement those virtual functions, and everything works out fine. And we use pure virtual functions here because this allows us to require the derived class implementing this interface to provide the necessary functionality. Great. Here's the problem with going that route. The problem with virtual functions from a performance standpoint is syntactically, we like to think about what's going on as, if the random number that we generated is less than the weight of the current node. That was the first step in the weighted random selection algorithm. We like to think that, you call weight of that node, and that just goes to a very simple method of the derived class to get the weight of that particular node. And that function is going to be tiny, and it's probably just going to get inlined. which is going to be really good for performance. Except that's not the way virtual functions work. The way virtual functions actually work is if this is in a method of the base class, what you have to do is get the this pointer, which is the pointer to the current object, go to that current object, which will store a pointer to the virtual function table for this class, go to that virtual function table, which will store a pointer to the function that you are about to call. So instead of just having a call where you say, I know exactly what function I'm going to, jump there, instead you have to go through this like multiple chain links of pointer lookups in order to find the function that you want to jump to. And you might say to yourself, well, that's just a couple instructions. Yeah, it's just a couple instructions, but it could have been one if it was going to be a function call. And realistically, it could have been way less than that if the compiler were able to know where this function call was eventually going to go when it was compiling this code here. Because if it knew, then it could just inline this function and say, oh, this derived class method is just looking up this field of this node. Maybe it's already got that in a register and you actually don't need to do anything. You just do the comparison because you already looked up the weight of this node very quickly and easily. This virtual function, though, forces the compiler to assume that even if it's compiling this code, and even if it thinks it knows what the derived class is right now, since this is a virtual function, at any point in the future, there may be a new implementation of weight of that needs to dynamically take the place of whatever version of the function the compiler can see currently. Now, all of this is nitpicking. From a broad performance standpoint, we're all talking about a handful of instructions, constant factors, but when performance matters, you can see these functions in some micro benchmarks that we've done. You can speed up this operation by, at least 2, if not 4 to 5x by avoiding using virtual functions for these small methods like this. Obviously, if this function is doing a lot of work inside of it, the overhead of doing these quick lookups to get into that function is insignificant. But if this is just a trivial field access function, you're easily making this function 2 to 5 times more expensive than it needs to be. Okay, so what could we do instead? This is the slightly brain-breaking, curiously recurring template pattern. The way that we're going to resolve this is to say, we are not going to use virtual functions. But if we're not using virtual functions, how can we call methods of a class that doesn't exist in the from the perspective of the base class of the weight sum tree class? And the answer is we pass it as a template parameter. We design our base class for the feature of a weight sum tree to take a template parameter, which will be the class implementing the concrete data structure. And then we can do things like this, which adds in a method that says, oh, and by the way, whatever class you provided as this template parameter, the current object, which is of type weight subtree, must be statically castable to a tree pointer. Oh, and once I've done that and casted it to a tree pointer, I must be able to invoke weight of on that tree with a given position. And then what we do to make that work on the inheritance side is heap random selector, instead of just inheriting from weight sum tree, we inherit weight sum tree, and then we pass in ourselves as the first template parameter. Hence the name, the curiously recurring template pattern. So we are basically breaking templates and using them maybe not exactly as they were intended, but as they were designed to be used, to basically give the base class information about what the derived class is, allowing us to write generic functions that we will then use template specialization to get the version of the weight sum tree class that is supported by the heap random selector class. And in that version of the weight sum tree class, the update weight function just calls the weight of function of the heap random selector class, and there's no ambiguity. There's no possible alternative of what function that could be. It must be the weight of function that belongs to the heap random selector class. No virtual functions required. So instead of using virtual functions as the way of requiring that a derived class must implement those functions, and using those virtual function interfaces as the hooks to invoke those functions, instead we're going to use a template parameter. And that template parameter, we're going to have this function which forces it to be a derived class, essentially. And then by using methods on that templated class, we specify the same interface. And so instead of getting compiler errors by not providing a virtual function, we will get providing compiler errors of an invalid template argument if you don't implement all of the features that you need in order for the weight sum class to work. Great. Once you wrap your head around it, it works. And once we've done this, all of the function calls are statically resolvable. The compiler has complete information of exactly what function is being called from exactly which other function. And then that unlocks a whole bunch of optimization that the compiler can do for us on our behalf. The problem is, as a developer, what happens if you make a mistake? Every C++ developer has had the experience of getting something wrong with a template parameter and having to go through, this one is actually not that bad. I just deleted or forgot one of the functions in the derived class. But everyone's used to dealing with pages and pages and pages of templated error messages and having to dig out what in the world went wrong to figure out what am I supposed to fix to make this work. And in this case, it's even more confusing because you were writing the derived class, the heap random selector, and you are being told that the error is in the weight sum tree class. And so you may think to yourself, oh, darn, there's a bug in the weight sum tree class. No, the bug is not in the weight sum tree class. It's just in the functions of the weight sum tree class that the compiler caught the intended misuse of the inheritance of the curiously recurring template pattern. We required that in this case, I think it was let's see if we can find the name, and where was it? Yeah, weight sum of. So weight sum of was being invoked in a function, and it needed to support const objects. This weight sum of function in the derived class only did not support a const argument or a const object, and we required a version that supported const. But the error is reported inside of the base class that is actually correct, not the derived class where we made the mistake. And yeah, this sucks. So In modern C++, knowing that this was such a big problem, one of the biggest things that was introduced, in my opinion, in more recent versions of C++ is the idea of C++ concepts. And C++ concepts are basically a way of specifying constraints and requirements on template parameters. Now, those constraints were being enforced already anyway. The problem was the error messages when those constraints were violated were incomprehensible and it was too difficult to figure it out. The main goal of concepts is to make it clear and obvious what the requirements of template parameters are. So you could, for instance, do things like this, where we say, oh, I require that the first template parameter here must meet the requirement of being a WST implementation. And that concept is defined here, which says, oh, it must inherit from a complete tree data class. I made this version up. It's more complicated than that, but this gets you the idea. This is a syntactically correct example, just not the one that we use in our code. So this helps a lot, and this is the intended use of C++ concepts to make sure that your template parameters actually follow the requirements of the class or the function that is setting up those template parameters for you. And if you do this correctly, then when your poor user or yourself 2 weeks later is trying to instantiate this template and does it wrong, the compiler will be able to give much more informative and useful feedback about how you instantiated this templated class wrong. That is the goal. Now the question is, okay, this was one example where we can say, oh, here's one requirement. We can require that this object here must derive from a particular class. That sounds nice. But remember, the goal of the curiously recurring template pattern was we wanted to make sure that this first template argument derived from this class, right? So can we do that? So here's the idea. We want to have our weight sum tree class with a concept that says the first tree, the first template argument here must meet this concept. We won't go into all the details of the concept, but instead of listing all of the abstract virtual functions that we did before that says a derived class must implement all of these, instead we list all of those functions in the C++ concept interface that I'm referring to here as is weight sum tree implementation. Great. Then we say that is the concept there. And then in heap random selector, we want to inherit from weight sum tree, and we pass in ourselves. And this should be fine because heap random selector inherits from the weight sum tree and implements everything related to the concept. Right? No. Here's what you are actually asking the compiler to do when you do this. You are asking the compiler to instantiate the heap random selector class. This is also templated because it depends on integer data types and such. So when you actually use it, you say, I want to instantiate a heap random selector class. Okay. To instantiate that class, you need to specialize and instantiate the weight sum tree base class for that templated class instantiation. When you specialize and instantiate the weight sum tree class and try to do the inheritance, you need to now verify that the first template parameters constraints are met. In order to do that, that depends on you having already instantiated the heap random selector class. And that is a circular dependency. You can't instantiate the class until you instantiate the base class, and you can't instantiate the base class until you verify that the constraint is met, but you can't verify that the constraint is met until you've instantiated your derived class. This doesn't work. You can't do this. This is actually not something that C++ concepts currently can handle. So because concepts are incompatible for the base class itself, like I said in the previous example, you could do something like this and require that this template parameter inherit from some other class, but you can't use a constraint that says this template argument must inherit from this class, because you can't instantiate the class until you've instantiated the derived class and it's a circular dependency. So this is at best a partial solution. Our implementation ended up using concepts where we could to ensure constraints that could be reasonably well checked, but it's also worth understanding and knowing the limitations of where these things can't work. And often it's, at least in my opinion, uncovering issues like this of where ideas don't work gives you the best idea, gives you the best learnings and understanding about how these language features really work, and how you can use them more effectively. So given that, in conclusion, what I wanted to highlight overall is that software design and software performance have to be considered together. There were times, and there are still times, where you will hear some people talk about, I don't care about performance. Software design is too important. I need to make sure that I'm designing my software well, and it doesn't matter that my software design choices might yield worse performance. I mean, there are situations where that is true. Performance is not always the most important thing about your software. On the flip side, there have been people who have said that software performance for this application is so important that I'm going to throw out everything that I've learned about good software design and just do what I need to do in order to make something that is really fast and efficient. And there are times where that can be reasonable as well. But for the vast majority of us going forward, we're not going to be able to pick and choose between them. We're going to have to do both. We're going to have to care about good software design principles like don't repeat yourself. Don't copy and paste code from one place to another. Have a well-organized class inheritance hierarchy to make sure that constraints are being met and that you can get good reuse and polymorphism out of the objects that you're working with. And at the same time, things need to be fast and efficient where possible. And that is where thorough, in order to do those sorts of things, this is a C++ conference. C++ happens to be my personal favorite language. And it does continue to be a language of choice for high performance applications. It's certainly not the only one. There are lots of other high performance programming languages that are worth considering. But C++ is certainly one that is worth knowing and continues to be widely used in this area where you care both about performance and software design, because C++ as a language has the features for you to support both of them. C++ features, though, like virtual functions, have performance implications that developers need to understand. In order to design for good performance, you need to understand the performance implications of the language features that you are using. And that goes beyond just what's the asymptotic complexity of this container class in the standard template library. Yes, you need to know that, but you also need to know, what does it cost to call a virtual function compared to a non-virtual function? And does that matter in my particular use case? And then modern C++ features like templates and concepts and the curiously recurring template pattern and these other design patterns can help further bridge the gap between good design and good performance. If you care about both of these things, it is possible to design software that is faithful to both of these principles and both of these value systems. But it takes work and intentional design thinking going into it. And it is not necessarily easy, as I've hopefully demonstrated in how even something like C++ concepts has fallen short in some areas where we would like to be able to use it. But understanding the way that your programming language environment works at a deep level is very important to being able to do both good design and good performance engineering. So with that, I will thank all of the people that have contributed to the work that I've done overall, which includes all of the co-developers of the weighted random selection code base, the fast code community that is building a lot of resources for teaching and learning software performance, and my two employers, Multicoreware and Whitman College, for supporting me in my research. And with that, Dheeraj, you want to jump in and start moderating questions?
Yep. Thank you. Thank you, John, for this wonderful, powerful talk. And now I request everyone to shoot your questions for John. Okay, and here we have our first question. I'll read it out. Is the performance benefit of eliminating a few instructions with sacrificing readability of code to this extent? Is it worthy?
That is a good question. And the answer is always, it depends. So first of all, I pursued this somewhat as a research project, and that was part of what I was trying to figure out in the design of this project is how much does this matter, and does this matter enough that people should be thinking about this seriously? The answer that we found is it depends a lot, and it's in context. So first of all, it's a few instructions, yes, but the question is, how many times are you invoking those few instructions? If you're invoking these instructions on small methods like getters and setters that you're invoking billions of times over the course of an application, it can make a big difference. Not because of those few instructions, but also, I didn't get into the details of this, but virtual functions hide a lot of information from the compiler. They hide a lot of information that the compiler could use to do even more optimization for you. So it's not just a matter of, oh, we're saving these couple of extra instructions. It is, if we give the compiler enough information, it can save not only those couple of instructions, but it can also inline, which gives it more information to do even more optimization. And there are situations where, yeah, these kinds of tweaks and changes can easily speed up an application by 2x or so if you get these things right.
Okay, so here is another question, which is, would singletons and gang of four still be relevant as we dig more into abstracts like attributes and concepts?
I mean, the short answer is yes. Like everything, all of our software design and software engineering concepts are still relevant. And it's just important to understand what are the language mechanics that you're using to implement those patterns, and what do those actually yield as a result? So, I won't talk about the singleton pattern specifically, or like the gang of four pattern specifically, because it depends on exactly how you implement them with exactly what language features. There's more than one way to utilize those software design patterns. And it's much more a matter of, I'm coming at it from the perspective, you know, people in here, I am assuming that many people in this call are way more versed in software design principles than I am. I'm trying to come more from a software performance engineering perspective and say, I know that these are things that we need to do in order to get good performance. How can we try to do that without giving up these good ideas that we've learned from software design principles? So yeah, I don't have enough expertise to be able to opine on, exactly how arbitrary software design pattern would interact with exactly these language features. But this is the kind of stuff that I'm really fascinated by and hope to learn more about and research more.
Yeah, okay. So there are two more questions here. I'll read out first one. In addition to the previous question, is it worth to compromise on readability by adding many portions of CPP code with assembly if it gives significant performance advantage for the use case?
It always comes down to trade-offs again. So let me give you an example. So at Multicoreware, one of the software packages that we're most widely known for developing is the video encoder, the video encoders X265, and we're working on X266 now. Oftentimes, those video encoders need to run on the newest hardware with the most performance. And this is true for machine learning workloads and applications as well these days. And for those kinds of workloads, for those kinds of applications, these are libraries that are incredibly widely used and incredibly performance sensitive. And so, yeah, it's worth us spending, as a relatively small company, it's worth us spending a few engineers, a few years of their lives on their time, really squeezing out the performance on these libraries because if you can if you could if an engineering team could reduce the execution time of all machine learning workloads in PyTorch by 10%, the economic impacts of that are huge. And so, yeah, sometimes it's worth it. A lot of the time it's not. Most applications, I would say, most applications you don't want to go to that level because it's just not worth it. The economic impacts of your application being half as fast as it could be is just not worth it's not worth the time and effort needed to improve its performance. And so you always need to be making those evaluations and considerations of how much performance do I think I could get, which you build up through expertise and consulting with people that have that expertise, and then asking yourself, is that performance worth the time and effort? There was a period of time, as I mentioned in the slides, where the universal opinion was no. It's almost never worth it. These days, I would say more and more, the answer is you should at least consider it and think about it. It may not be worth it, but it's at least worth doing the cost estimate to say how much work would it take to write somewhat better performing code. And it's not an all or nothing decision. It's not like you say, I care about performance, therefore I'm going to handwrite x86 assembly code with AVX intrinsics in order to get the best performance. Like, no, you start by taking the code that you have and making changes and improvements and enhancements to it. You make small compromises on software design. You make relatively low engineering effort investments to see, can you get some better performance out of it? And you constantly reevaluate, how much better performance did I get? How much more could I get if I think about it?
Okay, so we'll take one more question here before we'll move to Discord. So, do we need to take into the count the compilation time taken while using template in comparison to the C, as that is the baseline for C++?
Generally speaking, not so much. Um, Compilation time is something that matters, but the thing is, it matters for developers. generally speaking, compilation time is something that's going to affect you as a developer. It's not going to affect your users in the end. And the golden rule of software engineering is that your user's time is way more valuable than your time. Because, if you spend an hour of your time saving every user an hour of their time, that multiplies the economic impact by the number of users that you have. So, generally speaking, it's worthwhile for you to spend your time and effort to gain benefits for other people. That said, our time is also not infinite. And so it is something that you need to consider as well to say, okay, how can we design a workflow that doesn't, you know, every tiny code change that we make triggers a 1 hour build process to test, to get the next round of testing.
Okay, so there are few more questions, but I will request everyone to join the Discord channel where John will be there, and you can discuss that in detail, those questions. And thank you for John for this wonderful talk.